Fluid means fluid that flows, right? But if you take some sand and throw it, you just pour it on the table, that is also flowing, right? Is it a fluid? It is not, right? So you have to give a proper definition. Like, you give any small force, okay, then it moves, however small it is, however epsilon. You have epsilon thing, no? In your mathematics, real analysis, calculus, you must have done epsilon greater than 0, however small it is. So here also, however small force you give. Force means that usually shear. You just push it. Shear means horizontal force. Vertical force is also called normal stress. Okay, this is shear stress. That is normal stress. Normal stress is named as a pressure. Okay, so all these things, shears, stresses, normal or horizontal, all these things will come eventually when you are doing viscous fluid, when you are real fluids, when you are dealing. So before that, what you do is now you're only defining fluid. Fluid means something, some force you apply, and then it starts moving, it deforming, right? It changes its shape, right? So your sand, if you push also, even if while pouring, it won't change. You just give sand, no little bit change, nothing is moving. Maybe there is small change like elastic, right? Like elastic body, solid body, right? So it's not even solid. So that way, fluid is something you give any small deformation. You get a deformation even for any small force. So we write what exactly the meaning of it. Okay. So shear stress, if you apply, however small it is, there is a deformation. So the rate of deformation is actually gives depending on what kind of fluids you are dealing. Rate of deformation is within unit time, how much it is deforming. Okay. So within unit time, how much is defined? The rate of deformation. So that is exactly that goes from viscous fluids, it will be different. Inviscid fluids, it is different. So what are the fluids that you have? Usually, you see, fluids means either it is the immediate feeling is it's liquid or gases, right? So gases, you can compress it. You see, you try to pull them together, because the molecules are well separated there. Well separated means it's still gas, but it is separated. There is a gap between the molecules, huge gap compared to the liquids. Liquids, molecules, they're not much gap. So you can't compress it. So that's why this fluid is incompressible fluid or compressible fluid. So keeping liquids and gases in mind. Okay. So that is the property of the fluid. So compressibility is the property of the fluid. So we actually define what is a fluid and then look at the fluid properties first. Before that, we introduce exactly why do you need all these proper fluid mechanics? Why do you have to study? Okay. There's so many applications. We just try to list some of them. Okay. And then you guys are there, no? Hello?
Yes, sir.
Yes, sir.
Because you see, my full screen is with this whatever this board, this note. So I don't know. Sometimes if we lose the connection, I may not be able to see. Okay. So anyway, so you define fluids and you look at its properties, fluid properties. There are so many fluid properties that you have to understand. And first of all, to study the fluid properties, okay, but how are you going to see it? There is some assumptions you have to make to study this fluid. But that assumption is a continuum assumption. So if you look at gases and fluid liquids, you cannot put it in the same setup, right? So for example, you have to only under the assumption of continuum. Okay. Continuum means you're not going to see the molecule level. So you're going to see microscopic level, you're not going to see. You're going to see only macroscopic level. So fluids is okay. So every point you see that, you look at the molecules and an average, you calculate all of them within that small value. Okay. Let us say very, very small, minute sphere. That is a point, it's you take a point. Just a point in the space, no? That point is basically, imagine that it is a fluid. It's a liquid. Then you have a huge billions, some thousands of let's say lakhs. Okay, so thousands of molecules will be there. So there is not much gap. Even however small you take, you will still have enough molecules. On an average, how their movement, if you can do the on an average calculations, if you do, so you can see that enough molecules will be there, however small it is. But in the gases, still it will be there in the air. For example, in the atmosphere, when you look at up to the atmospheric air, you will have, however small it is, even though it is gas, you still have so many molecules, enough molecules. So however small you take, you still have billions, some thousands of molecules. So their averaging moment, if you consider moment, so you can safely assume that the macroscopic level, on an average, that whole point, that small sphere or whatever you think in R3, small sphere, epsilon distance, okay, that point it looks, any point it looks like a sphere, right? That sphere you consider as a fluid element, particle, fluid particle. Okay, that particle you assume that is, so that microscopic level only you're going to, not at the microscopic level like molecular level. So you only see this one. So that is what is the assumption of continuum hypothesis. Your hypothesis is, you assume that we only look at the macroscopic level fluid particles. You assume it is as a small spherical element of fluid. Okay, that you consider as continuum. That is a continuum hypothesis. Macroscopic level only you see at every point collection of all those molecules inside that sphere. You look at its movements. You, for example, if you are looking at its velocity, you look at all its movements, velocity, take it's an average. So you will have only that single particle velocity is like averaging of whatever all the molecules inside that. So that is exactly will give you. So you continuum hypothesis is that within that continuum hypothesis, once you consider, you can now work. Okay. Now, when this continuum hypothesis actually failed, if you go above the atmosphere, not exactly out of the atmosphere, even high altitudes, if you actually consider the air molecules, it is a different thing. So, for example, the fighter jets will go up, huge. Volume, it may not be enough. Once you make it very small quantity, you may see one out of some billions. You will see only one molecule out of the billions what you see in the atmosphere. So that is where that gap is so huge between the molecules, it fails there. Okay, so that is different. So, but you are going to learn as a mathematician. Just give you a feeling why this continuum hypothesis, where it fails, I'm giving you. Okay. So those things continue under this continuum hypothesis, and you are going to see what are the approaches that you do. You have to do mathematics, right? You have to model it. So there are two approaches. Either you follow is this particles, you look at it and follow it over time. One single particle you take, like that all the particles of the fluid. Okay, keep now just liquid in mind. So just one particle, one small sphere, epsilon distance, very dot. Okay,
Sir,
that is moving. Yeah.
sir, we are not seeing the screen which you are teaching, sir.
I shared, no?
Sir, we are seeing only the first page which you have written the books names. That is the screen we
That's
are
all.
seeing.
I'm not saying, I'm not writing anything. So I'm just orally talking only. Same thing
Okay,
only.
okay.
Okay. So these are the books. What I'm going to do. So that I will do maybe on 5th. On 5th, actually, I write down everything, whatever I see. And now overview, I'm just trying to give you feeling, because you guys are there. Almost 6 people are there. So just give you a feeling that, so that I'll feel motivated, and what you expect from the course. I'm trying to review. What do you expect from this course?
Okay,
Okay.
okay.
So we have a Lagrangian description of the fluids, or right, or there is something called Eulerian approach. Lagrangian thing is you follow the particle. So Eulerian approach is you try to I don't need to follow the particles. I stay at one particular point. You have a fluid. I just concentrate only at that particular particle. At the position of the particle, I look at it, and at that particular point only I concentrate. So what happens every time? When there is a flow, fluid is moving, fluid flows. What happens is that at that particular position, One particle will be there, immediately next instant there will be another particle. Like that will be, you're only watching that particle moving. Particle moment only you're watching at that particular position. Okay. So what you see is every time you have a different particle, and you have a different time is also there. So you have X, Y, Z, and T. All are independent kind of thing. Okay. So that you are trying to look at the function of these X, Y, and T. X, Y, Z, and T. Okay. Time is there, position is X, Y, T, and you are watching only one particle position. So at that time, one particle will come. Next moment, another particle will. So what is the difference? The change of, for example, if you're looking at that X direction, what is the velocity? You look at the X direction, what is the velocity? Velocity of the particle in the X direction. So that is, time is also independent here. X, Y, Z, and T are independent in that sense. But still, that means as a function of X, Y, Z. Okay, X, Y, Z, and T. So that X, if you just look at only X direction, if you look at it, then you will have a velocity in the X direction. So T and X, basically, they are like independent. So position and time are independent in the Euler. There it is different. X of T, Y of T, Z of T, and T. Where in your particle, you just follow the particle and observe. That is a Lagrangian description. So sometimes in fluid mechanics, those who are working, they use sometimes based on the convenience. Very rarely, some problems you may require Lagrangian description. That is rarely used, but otherwise most of the time for the equations and most of the times Eulerian description is easy. So whatever you do calculus you learned, no, that's what you follow in the Eulerian description. Okay, so those Lagrangian thing is like, +2 level you must have seen, what is the velocity, dx by dt, right? Change of dx by dt, dy by dt, all those are xy direction. So those are the components of velocity. Acceleration, if you want, 2 derivatives you do, but every time you have to do so that you know where your position is. You are seeing it as a function of t only there, all the components of x, y, t, and its derivatives, all those things. Like that, you have two descriptions, and we actually see that both of them are same. Okay, both the descriptions are same. So if you know one description, you can get the other description. What is the fluid property? Okay. Similarly, the other way, if you start with the Eulerian description, you can actually get your Euler Lagrange description. Like that, you can show that both are equivalent. And then we look at the fluid properties. Fluid properties like density, viscosity, velocity of the fluid particles. Okay, so whatever concerning about the fluid, you try to give, and then we look at what happens over time. These fluid particles. That is where you have the velocity, for example. So these are also property, but you give those material velocity. What is the usual temporal velocity, material velocity? If the fluid is moving and changing with time, that is where this is material derivative. It's a total derivative you might have seen in the calculus. That is exactly what you have here. Okay, Eulerian description, you will see that one. So those material derivatives, what is the definition? Basically, every time you bring in this calculus, a vector calculus that you need, because you're dealing with vectors. Sometimes eventually when you're going to viscous fluids, there you may need these tensors. Okay, so you have a relation between stress, two tensors, right? So stress and strain relation. So that's how you derive those equations. So okay, once you do this fluid kinematics, all the definitions and a little bit, finally mass, equation of mass, you derive the equation of mass also. Okay, because that is a kinematic, right? It's basically evolution equation. So what happens inside the fluid when it is flowing? You assume that there are three principles: mass is conserved, or Newton's second law, and then energy conservation. Energy is neither created nor. These are the equations. Is also valid in the fluid. So these equations, if you derive, these are the partial differential equations. That's what you have to derive. Derive means, how do you derive? Not for general right away. We don't do it for real fluid like viscous fluid. That is Navier-Stokes. That comes at the end. Right now we simplified. We take only, because you are learning, we only take the simplified equations. That means simplified fluid. Assume that is ideal fluid. I assume ideal fluid means you consider only compressible fluid. First of all, to do all these things, you have a simpler models like Eulerian equations. Euler equations only for incompressible fluid. Okay. Compressible fluid, you may have also, it's valid actually. Okay. So we'll look at the simplified models. Okay. Euler equations first of all. And then that is for ideal fluids. If you do it for ideal fluid, simplified Euler equations. Otherwise, Euler equations is also valid. That is only for, not for viscous fluids. Okay. So we will see as we learn. So at the end only you will have, so in every model, every simplified model, you will have these equations. You have to, the governing equations that you have to derive it neatly. Okay. Based on these fluid properties of that particular fluid, whether it is ideal fluid, as whatever, viscous fluid or inviscid fluid, incompressible fluid, or whatever, based on this, you will have to change the simplified equations will be there. So once you have only those things, then you try to look at the flows, simplified flows, so that where you do all these simple mathematics based on the mathematics that is developed during the development of theoretical fluid mechanics. Okay. Cauchy, Euler, these are the people responsible for that. So those are the people. So applied mathematics is developed along the way. So these are the mathematics, whatever mathematics you are going to learn. Once you learn this theoretical part throughout this course, then if you are actually working on some fluid mechanics, some things, tomorrow when you may do CFD, computational fluid dynamics, because of the advent of computers, these finally you are going to deal with these equations are nonlinear. Real fluid, if you consider, they become nonlinear equations. You can't go, whatever is developed mathematically only for simplified equations. Okay. So those only, that is done. The development, whatever is done mathematically, is done. Now you have a computers. So you'll have to take the main equations, the big, whatever possible real fluids, taking into consideration all the physical processes involved in the real fluids. Then immediately it becomes nonlinear. So you don't know how to solve mathematically also, you can't do anything. So you go for computations. Computations, that is why any real fluid, whatever in the aerospace, aerospace, you have now this wind flumes, air flumes, all those things, that's where you'll have to run it. You have to run these models on the computer, so that to see the flow patterns, for flow visualization, how it happening, all those things, that is different. So if you that you can pick up any fluid mechanics, advanced fluid dynamics, fluid mechanics books, and then see them. But all those things, if you really want to compute, you need to compute, or you have to do experiments. Experiments you can't conduct. No, it costs a lot, and computers are easy way to do. So there are two more things. One is theoretical, other one is this experimental. These were side by side developed, and then you can't do all experiments. So the computational fluid dynamics comes into picture, so that you can do anything. So all these things are simplified. Everything I compute now. So computation is very important in fluid dynamics. Before you do that, this is your basic course. You'll have to learn theoretical fluid dynamics, whatever little small things. So you'll have to have a feel of it, understanding of all the mathematics involved. Then only you can do that computational fluid dynamics. Then that you can do. You will do the justice when you are doing computational fluid dynamics, if you understand this theoretical fluid dynamics, or the mathematics, applied mathematics, whatever you have now, all those things you should understand from the course. Okay. Do you see the screen now?
No, sir.
Everything is blank?
No, sir. Now we can see, sir.
Yeah, because you see, I was only talking now, so that screen saver has come. So okay, fine. So that's so these are the textbooks I follow mostly. The outline of the course is what do you expect from the course I told you. Okay. Followed any questions up to here? In the process, when you look at this textbook, Cholton textbook, you may not like some of the text. So in that time, you just topic wise look into the other sources on the Google or whatever videos. Okay, whatever we teach, we may follow something else, simplified things only we follow, and make a note nicely. So whatever we are writing here, it will be there. Everything I write it here, whatever we learn. So it will be finally one kind of note for you. So I can share with you whatever I write here. I'll save it. Okay, it'll go like this. So right now, how many of you there?
Yes, sir.
I stop sharing. So let me see. Only same number, same nine are there. So 9 means 8 people are around. So you come back to the, by I think 50 will be in the campus, right? So that your internet also will be stable, and also you will have some books, whatever books I suggested, and we will, as you know, if you require, you also have library so that you can pick up some book. So you'll have a feeling of, when you start reading, you'll have a feeling. Okay. These are the things we learn from this course. Okay. So any questions you have? So we'll close it now. So we take only like this, only 1 hour, because it's 45 minutes. Any small concept you start writing now technically, you will follow and you will learn. So you give some time, and every time only 45-50 minutes. That's 1 hour, 1 hour, 1 hour will take. So for 3 days we'll do. Though it's given, for me, it's given 2-hour class today. I think it's not advisable for you to, because we're all mathematics guys, no? So you not really engineers already going through some fluid mechanics. It's not advanced course also. Just if you are directly interacting, that is a different issue. Whether we're following services also online, so we'll go slow. We'll learn. We'll try to learn whatever theoretical developments in the fluid mechanics in the early stages. So that is very important for you to continue to learn computational fluid dynamics or whatever, even to study numerical PDEs. Okay, whatever comes in the applications, you should have the feeling of fluid mechanics, eventually continuum mechanics, where solid mechanics also plays a role. Okay, so all these fluid mechanics, solid mechanics, if you are interested to study the PDEs, computational PDEs or whatever, these are the equations coming from this here. So at least little bit feeling you require. Okay, and whatever computations you are computing, math computing, math, you have a complete math in your hand, and then you also have a computation in your hand. So where do you do computation? Unless you have a feeling of physics. That physics is coming from fluid mechanics. There's engineering problems, engineering fluid mechanics or solid mechanics, overall continuum mechanics. So you should minimum understand, as an engineer, you're a BTech, right? So you're a BTech holder at the end of the day. So try to learn. Don't think that you're only in mathematics. You learn slowly, little bit mathematically you learn, and at the same time read fluid mechanics books as an engineer, because you're going to be engineer. So that feeling will come. So physics also one side, while reading you'll have. Okay, maths department, if you take all the courses, you may only mathematically you will be equipped. But are you taking some physics courses also in your curriculum?
In second semester engineering physics, sir.
Yeah, okay, that's okay. Yes, that's what is required. Usually they'll include everything, because you're BTech, no? So yeah, as an engineer, you should go complete engineer. You have to go out. So I try to give what I understand. Okay, so from as a mathematician point of view, how do you have to understand? This is applied. This is a kind of applied mathematics. Okay, so we do applied mathematics, whatever required mathematics to understand the fluid mechanics or fluid dynamics, basically. Or in general, you need to understand a little bit of solid mechanics also, if you happen to study in future. So those equations are important. Finally, PD. Suddenly you look at the equations, right? Equations are all coming from these applications only. Fluid mechanics or solid mechanics or whatever. From that only you get those equations. So and then you look at the equation. What kind of equation? Linear equation, nonlinear equation, or linearized it, simplified. Look at its linearized version. What are the results? And you try to include those complexities and try to solve it. You will not have methods to solve, because it's once you bring in nonlinearity, you only have to go for the numerics. You have to understand the computations, right? You need to understand the schemes, how the schemes work, numerical schemes. Okay, computation means simply computation will not do. So you have to develop some schemes. The schemes, you have to look at the stability of the scheme, how it's working. You have to understand the scheme before you apply it. Otherwise, you do the computation, at the end you lost, you are getting some junk. You don't know where you have done the mistake. So you have to understand the schemes. That's why the numerical schemes are developed for the PDEs. So all these things you have to master it before you come out of the your course, your program, BTech program. So in the process, this is the one component. You have to understand theoretically, all the fluid mechanics, fluid dynamics concepts. Okay. And the side by side, you have to link with computation schemes and all other things with other courses, and you have to link up. Okay. So anyway, so we'll see. So I hope to see all of you in the next class on 5th. Okay, 5th at 11 o'clock. 11 to 12 we'll have. So that time we will start writing exactly whatever we start right from the beginning. Introduction, fluid properties. Okay. So one by one properties, and then see what exactly these hypotheses and different descriptions of the fluids. All those things we will see. Okay. So ask me if you have any questions at the moment. Yeah. You don't have?
No, sir.
Do you have class now after this? Hello?
No,
These
sir.
classes are, you have classes going on online? Only this class?
Yes, only this is first class, sir.
First class.
So
Okay, okay.
tomorrow we
So,
have another class.
all right, all right. So no problem. So once you come back, we will see. That is anyway next week. So you will be, in your mind also will be academic environment, which you will be in the campus. So we can actually start. So I just try to motivate the description of what we do in this course. So hope you now look for some simpler materials on Google. Just look for what is that you do. Children book, you may find online as at least contents. You look at the contents and see, and what your in general, what is the fluid dynamics, what you expect from the course, what they teach on Google. Videos also, you see so many videos are there, content wise, right? Based on the things, if you follow one book, you will have to follow their notations. Okay, something complicated they have written, some mistakes are there, they may not, don't like it. So somebody must have written easily the same theorem. So you try to learn whichever way and try to make your own notes. So that this is all nice way, what your understanding way you have learned. That is the way to learn. You don't have to follow one book. But as a textbook, you keep it the same. For example, I don't like one on whatever written on topic there. I learn somewhere else and I see that. Then I come back here and you may see that, yeah, it is written nice. Oh, now we don't understand. Sometimes when you read, you may not understand. But to look for the same information is a simplified way by the teacher or some other resource. So then you come back to the same textbook that you have and then you follow it. So that's how you learn. Learn and keep the one textbook. Now I know at the end of the day, you should be able to understand one textbook so that you don't need to carry all the textbooks with you in your future. So keep one textbook because now you have the notes and you know the where you picked up those other in between certain topics you might have learned easy way, so that you know where you have learned. That you can always go as a reference. Because wherever the reference that you can write in your notes, and you have a textbook. So throughout life, if you are using it as a career, that's how you normally usually you keep it. So whatever you learned at this stage, at the early stage, that is the textbook usually you follow even when you are working research, in higher education or whatever. That time you'll be referring only what you learned in your UG. Okay. So hope see you again on 5th. If you don't have questions, otherwise just stay and ask some questions. Okay. If you don't have questions, please leave. If you have questions, please ask.